Hey there, guys. How you doing? It's time for topic 3.04, gases and pressure. Okay, so we really haven't delved too deeply into the phases of matter, and we're going to be spending the rest of this unit looking at one phase of matter in particular, gases, because they're really, really interesting and you can do all kinds of cool stuff with them. So, can you handle the pressure? Now, the definition of pressure, what exactly is it? Well, there's emotional pressure, where you feel pushed on all sides to get something done. But the scientific definition is pressure is force exerted over an area. So, what exactly does that mean? Well, first of all, this is not the kind of force I'm talking about. Not that kind of force. I'm disappointed. No, given equal force, if you exert it over a smaller area, that would be greater pressure. Imagine being stepped on by somebody wearing these shoes. Notice the small area that the pressure is being exerted over versus exerting it over a larger area. All that force is now exerted over a larger area. This is why things like needles and pins and nails are all pointy at the end, because the force you exert on one side has to pierce through something on the other side. And the smaller you make that other side that's doing the piercing, the less force will be required to actually drive that into whatever. Like if you're going to hammer a nail into a piece of wood, imagine that the nail was flat on the end going into the wood. Well, that force that you're hitting with the hammer is now spread out over a wider area. So you're going to have much less impact on getting that nail into the wood. So you're going to have to hit a lot harder to drive that nail into the wood. Imagine that you're going to get a shot and the needle they use is flat. Okay, there's going to be a lot of pain involved. So what they do is they make that end really, really pointy. The pointier they can make it, the less pressure it's going to take to get that needle to go into your skin, or the less force it's going to take to get that nail to go into the wood. So that's a practical application of pressure from a solid perspective. Now, how do we measure pressure? Well, since pressure is force over an area, we're going to have a unit that has force and area. Our atmosphere exerts 14.7 pounds over every square inch of surface at sea level. You see, we have a lot of air in our atmosphere, and air, being matter, has mass. It's like a big blanket of gas covering our planet. And that gas exerts force over its surroundings. Pounds would be the unit of force. Square inch is the unit of area. Pounds per square inch. 14.7 of them. That is a lot of pressure. It can actually push a column of a very heavy liquid metallic element, mercury, up a barometer tube to a height of more than half, actually 3/4 of a meter high. This is a diagram of a barometer. We have a pool of liquid mercury, and we have a tube that's had all the air removed from it. So there's nothing pushing back inside the tube. Air can push down on this pool of mercury and push it up the tube until the weight of the mercury equals the weight of the air pushing down. And the column of mercury at normal pressure on Earth is 760 millimeters high. This device was invented by one Evangelista Torricelli, and as such, a millimeter of mercury is also referred to as a torr. 760 torr is 1 atmosphere of pressure. We use Earth as standard because we live here. So 1 atmosphere is 760 millimeters of mercury, or 760 torr, but there are other ways to mention it as well. kilopascals. These are related to the millibars that you learned about in earth science. 101.3 kilopascals is 1,013 millibars, or 1.013 bars. So there's many different ways of measuring. You have newtons per square meter, for example. There's many ways of measuring pressure, but the two standard ones that we will make use of in this course are atmospheres and kilopascals. So if you want to convert atmospheres to kilopascals, multiply by 101.3. And if you want to convert kilopascals to atmospheres, divide by 101.3. You'll see how the numbers cancel each other out. If you want to convert atmospheres to torrs, multiply by 760. If you want to convert torrs to atmospheres, divide by 760. So it evens itself out very nicely. Now, again, 3.5 atmospheres is how many kilopascals? 212 kilopascals equals how many atmospheres? Well, divide this by 101.3. I'm sorry. Multiply this by 101.3 and you'll get kilopascals. Divide this by 101.3 and you'll get atmospheres. You want to convert atmospheres to torrs? Multiply by 760. You want to convert torrs to atmospheres? Divide by 760. Okay. Now, gases have to have predictable behavior if we want to do any kind of math. There are what are called gas law equations. Now, all gases are different. And remember how I said that gas molecules have no attractive forces? Well, that's not strictly speaking true. Their attractive forces are extremely weak, and the molecules are too far away from each other and moving too fast to do anything about it. If you cool a molecule down, if you cool a sample of gas down, the molecules will move slow enough that they get closer together, and then the attractive forces can kick in and condense the gas back down to a liquid. But in order to make the math for gases easier, we're going to assume that gases are ideal, that all gases behave the same way, because if we assume that all gases behave the same way, we can apply exactly the same math regardless of what gas we have. So the kinetic molecular theory describes the behavior of this mythical ideal gas that will make our math easier to do. First, gas is made of molecules that are far apart and small. Now, hydrogen and helium are the molecules that have the least volume on the periodic table. And therefore, even though they are not ideal gases, they behave the most like we would actually predict an ideal gas to behave. Ideal gases would ideally have no volume at all. Each molecule would be infinitely small. That's impossible. So the smallest gas molecules there are would behave the most like ideal gases, even though they're not really ideal gases. Gases will behave most ideally when they're the furthest apart. So you want high temperature because gases will expand when you heat them, making the molecules further apart, and low pressure because at low pressure, the molecules are further apart. So at high temperatures and low pressures, and the smaller the gas molecules are, the more ideally a gas will behave. So gas is made of molecules that are far apart and small. They don't lose their energy when they hit container walls. Now, what this means is that if a gas molecule hits a container wall, it will maintain the same speed it had before it hit the wall. It won't slow down. If gas molecules hit each other, one gas molecule might slow down by a certain amount, but the other gas molecule will speed up by the exact same amount that the other molecule slowed down. So if one molecule loses, let's say 5 miles per hour in speed, the other gas molecule will gain 5 miles per hour in speed. So the overall average speed of the gas molecules will not change. These are called elastic collisions, collisions that conserve energy, collisions where no energy is actually lost. So, gas is made of molecules that are far apart and small. They don't lose their energy when they hit container walls. They travel in a straight line, no changing from their course. See, this is called inertia. An object in motion will continue in motion until acted upon by an outside force. Gas molecules will continue in a straight line until they hit something, and then they'll bounce off. So, gas is made of molecules that are far apart and small. They don't lose their energy when they hit container walls. They travel in a straight line, no changing from their course. They move faster when it's hotter. They have no attractive force. Now, real gases do have attractive forces, but we ignore them because the molecules are moving too fast for the attractive forces to take hold. But the perfect ideal gas would have no attractive forces at all. So, as long as you remember the kinetic molecular theory, then you'll understand how the gas laws operate. So, any gas that behaves like this are called ideal gases. There are no such gases in the real world. All gas molecules take up at least some volume. All gas molecules have at least some attractive forces. So, there are math equations that take that into consideration, but it makes the math a whole lot harder. I'm going to show you that when we do the last topic of the unit called the ideal gas law. Okay. Most gases will behave fairly ideally at standard temperature and pressure, abbreviated to STP. STP, gases aren't going to behave most ideally, but they behave ideally enough for us to use gas law equations, simple gas law equations. What are the conditions at STP? STP, the temperature's 273, the pressure's 101.3. STP, you can use it in chemistry. You can find it on New York State Reference Table A. Standard pressure in both kilopascals and atmospheres, and standard temperature in both kelvins and Celsius. This is not when a gas is most ideal, but this is when most gases are ideal enough for us to get away with using the simple math formulas we're going to use later in the unit. Avogadro's hypothesis describes one really neat feature of ideal gases. Since we're going to assume that all gases behave exactly the same way, we can make the following assumption. By the way, this is Amedeo Avogadro, who not only came up with Avogadro's hypothesis, he also figured out how many atoms there would be in 1 mole of atoms. Avogadro's number, 6.02 times 10 to the 23rd. We'll look at that value more when we do the compounds unit later on. If you have 2 samples of an ideal gas, and it doesn't matter what the gas is made of, but we're going to assume they're ideal, and they have the same properties of volume, temperature, and pressure, then you can assume that both samples will contain the same number of molecules. So if we have 2 samples of different gases that are both ideal, they both are at the same temperature and pressure, and both occupy the same volume, we can make the assumption that both samples of gas will contain identical numbers of molecules. This is also going to allow us to use the gas laws with any gas, assuming that it's an ideal gas, which again, no gas really is, but if you make that assumption, it makes the math easier. You'll find that that's true in a lot of science situations, that we have to make assumptions to simplify things to make the math not make us want to tear our hair out. So, which 2 samples of gas contain the same number of molecules? Well, have a look. Which 2 samples of gas have identical volume, temperature, and pressure? Because if their volumes, temperatures, and pressures are the same, we can assume that the number of molecules is also the same. 2.0 liters, 300 Kelvin, 3 atmospheres. 1.0 liter, 200 Kelvin, 2 atmospheres. Well, these obviously do not contain the same number of molecules. 3 liters, 200 Kelvin, 3 atmospheres. 2 liters, 400 Kelvin, 3 atmospheres. So far, they've all been different. 2 liters, 300 Kelvin, 3 atmospheres. This is the same as oxygen. They both have 2-liter volume. They both have 300 Kelvin temperature. They both have 3.0 atmosphere pressure. Since all three conditions of the gas are identical, we can assume that both samples will contain the same number of molecules. Okay, that's Avogadro's hypothesis. And that is the end of this presentation. Next up, evaporation and vapor pressure. Ooh, I can hardly wait. So until next time, have a delightful day and bye.